Hello everyone, welcome to the Tim Booker channel. I wish you all a pleasant listening experience. Today, we delve into The Perfectionists by the British historian Simon Winchester, with the subtitle, How Precision Engineers Created the Modern World. At the beginning of the book, Winchester recounts a memorable incident from his childhood. During a Christmas dinner, his father, a precision manufacturing engineer, presented him with a mysterious little box containing square metal blocks, smooth, shiny, and each engraved with a unique number. The author vividly describes how his father stacked two metal blocks together and challenged young Winchester to separate them. Despite his efforts, the blocks seemed almost fused together due to their incredibly smooth surfaces, creating a vacuum that resulted in a powerful adhesive force. These magical metal blocks, as his father explained, were called gauge blocks. Similar to rulers or weights, they play a crucial role in industrial manufacturing by measuring the tolerances of parts, the minute variations between each part's dimensions and manufacturing standards. If the error exceeds a very fine standard, the part is deemed defective and unfit for use. Influenced by his upbringing in this environment, Winchester developed a deep fascination with precision manufacturing from a young age. In his eyes, precision is an indispensable component of various cultural landscapes in our modern society, emphasizing its paramount importance to industrial development and human civilization. According to Winchester, precision is the fundamental driving force behind the development of modern technology and manufacturing. The term precision originated from Latin, meaning separation, cutting, trimming. This definition may conjure an image of a craftsman sitting at a workbench, meticulously processing and polishing components to meet the exact standards of a design blueprint. From the perspective of industrial manufacturing technology, precision implies perfect alignment with certain standards, and these standards, such as tolerances we mentioned earlier, continuously narrow. For instance, John Wilkinson, hailed by Winchester as the father of precision manufacturing, in the 18th century, achieved a tolerance of only 0.1 inch or 0.254 centimeters, nearly the thickness of a coin, in the machining of steam engine cylinders using his invented boring machine. Although this precision seemed remarkable at the time, today's high-precision lithography machines, such as those manufactured by the Dutch company ASML, achieve accuracy to 1,000th the diameter of a human hair when burning chip circuit diagrams onto the surface of silicon wafers using ultraviolet light as a brush. In summary, since the advent of the industrial civilization era, precision has become a timeless pursuit for humanity and a golden standard for measuring a country's comprehensive technological strength and civilization. Tian Tao, a management consultant at Huawei, wrote an enthusiastic preface for the Chinese version of this book. He summarized that the book is not only a history of the evolution of precision manufacturing over 250 years but also an innovation history of humanity continuously approaching the limits of precision. It stands as one of the most heartfelt and time-consuming works in his reading experience. In the following sections, I will guide you through Winchester's narrative in two parts, exploring the extensive journey of humanity in The Perfectionists. First, we will examine how the concept of precision was born during the initial two industrial revolutions in the 18th to the first half of the 20th century, leading humanity into the centimeter and millimeter precision era. In the second part, we will explore how, with the advent of the electronic industrial revolution, humanity's pursuit of precision entered the micro and nano era. We will also examine how the resulting new technologies and industrial products have influenced human life and exploration of the unknown world. Alright, let's turn the clock back to mid-18th century England and visit the man hailed by the author as the father of precision manufacturing, Wilkinson. According to Winchester, Wilkinson made crucial contributions to the birth of the Industrial Revolution, though his achievements were overshadowed by a friend and client of his, the inventor James Watt, renowned for improving the steam engine. However, without Wilkinson's technology, Watt's success would have been impossible. Here's the story. In 1775, Watt and Wilkinson joined forces due to a business collaboration. At the time, Watt was fine-tuning his first improved steam engine but faced a significant problem: steam continuously leaked from the cylinder when the engine was in operation. Upon inspection, Watt discovered that the up and down movement of the piston did not fit snugly against the cylinder walls. Gaps in some areas caused steam leakage, while in others, the piston was too tight against the cylinder, resulting in significant friction and wasting the precious energy of the steam engine. What sought the expertise of Wilkinson, nicknamed the Iron Madman, who had obtained a technical patent for his precision boring machine. This machine, similar to a hydraulically powered drilling machine, could rapidly and precisely drill a straight, smooth-walled hole in a metal cylinder, transforming it into a hollow metal tube. Soon, this emerging industrial processing machine was used to mass-produce firearms. Gun barrels manufactured with the boring machine outperformed those cast with molds, exhibiting superior performance and durability. Although the hydraulic-driven boring machine was much more efficient than manual labor, Wilkinson was not satisfied. He aimed to find a more efficient way to drive the boring machine. Conveniently, Watt approached Wilkinson with the idea of using a steam engine to power the boring machine, further increasing productivity. Since Watt's steam engine had flaws in the cylinder's dimensions, and the cylinder's shape resembled that of a cannon, Wilkinson believed his boring machine could address this issue. Therefore, helping Watt also meant helping himself, and Wilkinson eagerly agreed to the collaboration. As Wilkinson expected, his boring machine produced perfectly sized cylinders with an error margin of less than 0.1 inch according to the specifications. Watt's steam engine smoothly operated with these precise cylinders. Instantly, the steam engine evolved from a laboratory toy to a widely applicable universal production tool, liberating economic production from the shackles of nature. In Winchester's words, with the use of the steam engine, a new world was created where machines could rapidly produce the needed products, and machines could be used to manufacture more machines. From this moment on, precision became the most crucial quality and measurement standard in this novel production mode. Only by continuously adhering to the principles of the Perfectionists could complex mechanical devices run smoothly, continuously creating wealth for humanity. However, besides the pursuit of wealth, war and conflict served as another major driver stimulating rapid technological development. The technological expert we will introduce after Wilkinson, whose inventions quickly spread and elevated precision manufacturing to new heights, owes much to the industrial era's massive demand for weapons in times of war. First on the scene is a technician named Maudslay, who made significant contributions by improving the lathe, expanding the possibilities of precision manufacturing even further. Maudslay initially used metal to manufacture lathes, providing both weight and durability. This allowed the lathe not only to process metal products but also significantly increased its stability, preventing vibrations during processing and ensuring precision. Additionally, Maudslay invented a lathe component called the sliding carriage, which could carry various tools for processing metal, such as cutting, drilling, and polishing. The sliding carriage's position could be finely adjusted both vertically and horizontally, theoretically ensuring that metal parts produced by remembering the sliding carriage's precise position would have identical specifications. With metal lathes and sliding carriages, what level of precision could workers achieve in the early 19th century? The author gives us an example. For common screws found in various mechanical devices or daily consumer products today, Maudslay's improved lathe could reduce the tolerance between each finished screw and the design standard to an astonishing 1/1000th of an inch. At that time, Britain was fully engaged in the Napoleonic Wars. A significant strategic focus for Britain was using the Royal Navy's absolute advantage to blockade Napoleon's rule over France and the European continent, disrupting France's maritime trade and transportation and defending against potential French invasions. To achieve these goals, British shipyards needed to work at full capacity, producing a large fleet. Since warships at the time were still wooden sailing vessels, each ship could not do without an essential component, the block. Essentially, a block is a complex lifting system composed of pulleys, frames, and cables, used to control numerous sails on the ship. According to statistics, controlling a large warship required over 1,400 block sets. To maintain the smooth operation of the vast Royal Navy, factories needed to manufacture over 130,000 blocks annually. Before the advent of improved lathes, skilled artisans manually crafted these blocks, resulting in very low efficiency. Consequently, Maudslay was hired by the British Admiralty to design a production line consisting of different lathes, all driven by Watt's improved steam engine. This lathe production line, requiring a minimum of 10 workers to operate, effortlessly achieved the annual production of 130,000 blocks, with excellent quality surpassing even the most skilled carpenter artisans. One can imagine that with the introduction of various new technologies and manufacturing equipment, the precision of products has continually increased. The gaps between products, as well as between products and blueprint standards, have become smaller. This not only enhances product durability and interchangeability but also lays the foundation for the next significant industrial manufacturing revolution. The core of this industrial revolution is the assembly line production. When discussing it, we cannot ignore a classic product in two key figures. The product is Ford's Model T automobile, and the protagonists are Henry Ford, the founder of Ford Motor Company, and the Swedish individual mentioned earlier, Johnson. Speaking of Ford, his ambition and foresight aimed to transform automobiles from a luxury item exclusive to the upper class into an affordable means of transportation for the ordinary American. In 1907, he convened his engineers to design a groundbreaking product. Ford set strict requirements for this new car: spacious enough for 5 people, robust, easy to drive, adaptable to various road conditions, and, most importantly, priced affordably. Consequently, on October 1, 1908, the first Model T car officially debuted in the Ford factory. Due to its superior performance and low cost, it sold 16 million units in the following 19 years. Many users are likely aware that the success of the Model T lies in Henry Ford's use of the assembly line production method in his factory. Each worker on the production line only needed to perform a basic, uncomplicated processing operation on the component in front of them. Finally, at the end of the assembly line, a complete car was declared finished. However, for the assembly line production method to be implemented, there was a crucial prerequisite: all structural components and parts of the cars had to be sufficiently precise, with errors strictly within a predefined tolerance limit. The same type of part from different cars should easily interchange. This way, untrained workers on the assembly line wouldn't need to inspect meticulously, they could mechanically complete simple assembly actions, quickly producing one stable performing vehicle after another. In other words, if a considerable number of components or parts had defects or specifications beyond the preset tolerance, the entire production line would frequently jam, and efficiency would plummet. Although, to achieve mass production on the assembly line, a Ford Model T only had slightly over 100 components, this new production model encountered some difficulties in its early stages. For instance, due to the expanding market demand for the Model T, the production of many components had to be outsourced to other manufacturing companies. As a result, a Swedish ball bearing manufacturer named SKF frequently caused production line stoppages and jams when its components entered the Ford automobile assembly line. Henry Ford was furious and confronted SKF's management. However, upon closer investigation, it was discovered that SKF's ball bearings had higher precision than those produced by Ford himself, leading to frequent assembly line jams. So, surprisingly, it was Ford who needed to improve the technical standards. So, why could SKF's products achieve superior precision? The answer lies in SKF's product testing, where they initially used the Johnson gauge we mentioned earlier. As we mentioned before, Johnson was a quality inspector at a Swedish firearms factory. Once, while traveling by train, he pondered the question of how to manufacture a set of gauges for measuring product dimensions in a factory. He arrived at the answer before getting off the train: 103 gauges. Any 3 gauges taken from this set could be arranged in various combinations to achieve a tolerance of 1/1000th of a millimeter in product dimensions. After hearing this news, Henry Ford used his financial resources to address the measurement precision issue with his car parts. The solution was to buy Johnson's small company outright, relocating it from Sweden to Detroit, where it became a department under Ford Motor Company. It can be said that the victory of the Model T, and even the success of the entire Ford Motor Company in the early 20th century, was largely a triumph of precision manufacturing standards. Alright, we've just explored how precision manufacturing technology has emerged and evolved since the Industrial Revolution through a few examples. Over the next century, the standards of precision manufacturing and the complexity and performance of human industrial products have mutually propelled each other, spiraling upward. The improvement in precision allows various high-tech products to have increasingly complex internal structures and leapfrog in various functional indicators. The increasing complexity of high-tech product structures, in turn, imposes higher requirements on the precision of their individual components. In this section, the author, Winchester, guides us into a new era where precision is measured in micrometers and nanometers. To provide us with an intuitive impression of how important precision is in the high-tech era, Winchester spares no effort in narrating a significant scientific mishap caused by a deviation in precision. The main character of this incident is the well-known Hubble Space Telescope. In a nutshell, a size deviation of 2.2 micrometers nearly rendered the $2 billion Hubble Space Telescope useless. 1 micrometer is equivalent to 1/1,000,000th of a meter, and the diameter of a fine human hair can range from 60 to 90 micrometers. One might wonder why such a small error had such severe consequences. To answer this question, Winchester first takes us through a brief history of the development of optics and lenses. In essence, to obtain clearer, more realistic images of distant objects, the structure, materials, and processing precision of lenses, which are the core of photographic equipment, have been continuously advancing. Winchester informs us that nowadays, optical engineers, like conductors of an orchestra, combine glasses with different components and optical properties, striving to achieve the best anticipated optical effects. To reach the ideal level, lenses incorporate various rare earth elements, and even non-glass materials are embedded. The number of lenses inside a lens is also continually increasing. Simultaneously, the processing precision of the lenses themselves is continuously rising. For example, renowned camera brands like Leica achieve a surface processing tolerance for their lenses at a staggering 500 nanometers, which is 0.0005 millimeters. In other words, to ensure that an ordinary user captures satisfactory travel photos, the surface processing of a camera lens needs to achieve this level of accuracy. So, for an astronomical telescope like the Hubble, aiming to precisely capture images of distant planets in space, the requirements for the precision of its lenses can be imagined. Winchester states that the main mirror of the Hubble telescope has a diameter of approximately 2.4 meters, and the precision requirement for its surface contour is 1/1,000,000th of an inch. In other words, even if the surface area of the lens is magnified to be as large as the entire Atlantic Ocean, the tolerance anywhere on the surface would not exceed 10 centimeters. On May 20, 1990, after about a month in space, the Hubble Space Telescope began its work in orbit. However, the eagerly awaited photos received by astronomers turned out to be uniformly blurry, rendering them scientifically valueless. The reason for this situation was a 2.2 micrometer machining error on the edge of the Hubble's main mirror. This minute error occurred due to a bizarre reason. To precisely calibrate the dimensions of the lens, technicians used a device worth several $1 million called the null corrector, which utilized laser reflection for accurate measurements of the mirror's surface. This process was expected to be foolproof. However, to measure the distance between internal parts of the corrector, the staff had to use a metal rod. Unexpectedly, due to surface coating wear on this metal rod, a 1.3 mm error occurred in its dimensions, directly resulting in the ground mirror of the telescope being out of size. This is analogous to meticulously trying to draw a precise line but realizing the ruler itself is incorrect. Due to this processing error, the Hubble Space Telescope effectively became nearsighted. To compensate for this mistake, technicians had to re-enter space and install a set of optical correction devices inside the telescope. This optical correction set is akin to putting contact lenses on a nearsighted eye, correcting its vision. Winchester says that from a macrohistorical perspective, the timing of the launch of the Hubble Space Telescope is quite interesting. The technology and complexity required to manufacture it indicate that precision manufacturing has reached a limit at the visible level using traditional mechanical equipment. With the development of computers and electronic engineering, the next step in precision manufacturing has entered the microscopic world that is difficult for the naked eye to observe, the world of atoms and electrons. The representative of precision manufacturing in this microscopic era is the computer chip and the lithography machine used in chip manufacturing. About the revolutionary technologies of the information age, if you're interested, I recommend 2 authoritative works on related topics, The Chip War and The Lithography Giant. Due to space constraints here, let's briefly review their development from the perspective of precision manufacturing. Simply put, a chip is an integrated circuit made from a small piece of semiconductor material, usually silicon, with a certain number of transistors integrated on it. Transistors convert electric currents into switch signals, enabling digital calculations. Driven by the rapid development of missile technology, automatic control, and aerospace during World War II, there was a sharp increase in the demand for data calculation and processing. This led to the birth of electronic computers. In the subsequent years, as the application areas of computers expanded, the demand for computing power increased. To accommodate these complex tasks within the limited surface area of chips and electronic devices, the only solution was to make transistors smaller. People familiar with the computer industry might recognize the term Moore's Law, which states that every 2 years, the number of transistors on a chip of the same size will double, and the computational performance of the chip will also double. Winchester gives an example in the book. In 1971, Intel, a chip giant, introduced the famous 4004 chip, which housed over 2,300 transistors with distances between them in the micrometer range. However, merely half a century later, the A14 chip used in the Apple iPhone 12 could accommodate 11.8 billion microtransistors on a surface area of 88 square millimeters, with gaps between these transistors reaching the nanometer range. 1 nanometer is 1/1,000,000th of a meter, even smaller than the diameter of a single new coronavirus particle. Compared to this precision, the early cylinders on Watt's steam engine, parts of Ford's Model T car, and even the lenses of the Hubble telescope are overshadowed. With such precision that cannot be achieved by the human eye in traditional mechanical equipment, what is relied upon to achieve it? Any processing tool made of physical materials is not dependable. Therefore, the solution lies in the magic of light. In September 1958, a U.S. physicist named Lyon Roger Lupou was troubled by the oversized dimensions of the chips he was developing, making them unfit for devices. One day, while observing transistors on a chip through a microscope, he had a brilliant idea. Since the original function of a microscope is to magnify objects, if the microscope were turned upside down, something large would undoubtedly be reduced. Following this principle, if a chip circuit diagram were placed at the objective end of a microscope, a significantly reduced version would appear at the other end. Lupou was excited about this idea, but he didn't stop there. He thought about a photosensitive resin invented by Kodak, called photosensitive resist. This material hardens and becomes easy to remove when exposed to light. So, if a beam of light passes through the microscope lens covering the chip circuit diagram and is then directed onto the surface of a semiconductor covered with photosensitive resist, after washing this semiconductor block in a special chemical solution, the photosensitive resist that has been illuminated by light will harden and peel off, while the underlying part will be corroded. Consequently, the chip circuit diagram is precisely etched onto the semiconductor surface, like a small maze. Next, inject materials like phosphorus and boron into this miniature maze, and transistors will naturally form at each node. Lupou's ingenious idea for manufacturing microchips was named lithography, and the photosensitive resist, once used for making film, got a new name, photoresist. The lithography method enables the convenient and precise mass production of chips. While the size of chips is significantly reduced, they can accommodate more transistors. It can be said that Lupou's invention of the lithography manufacturing method laid a solid foundation for the continuous improvement of computer efficiency. Without lithography manufacturing, various technological achievements of the past decade, from moon landing and the internet to artificial intelligence, would not have been possible. Today, manufacturing chips using the lithography method requires the use of structurally super-complex lithography machines. High-end lithography machines manufactured by the industry giant ASML in the Netherlands have as many as 100,000 components, with a single machine costing over $100 million. If we imagine light as a carving tool, the shorter the wavelength of light, the sharper the tool. In news reports, we often hear about advanced computing chips reaching certain nanometer standards. What does this mean? For example, a 7-nanometer chip means that only a few nanometers separate each transistor on it, equivalent to 1/10,000th of the thickness of a human hair. To manufacture such chips, a special kind of light, extreme ultraviolet light, is required. Its wavelength is only 13.5 nanometers, which is a fraction of the visible light wavelength. Effectively controlling extreme ultraviolet light is challenging because it can only propagate in a vacuum and cannot be focused or reflected by a lens like ordinary light. It can only be obtained using an expensive device called a Bragg reflector. The method, sounding somewhat crazy, involves emitting powerful laser light toward high-temperature gaseous metal to obtain it. These miraculous rays moved down through multiple reflectors in the lithography machine and finally reached the silicon wafer for etching. The tolerance can be maintained within the astonishing range of a few billionths of a meter. At this moment, humanity's pursuit of precision and the means to achieve it have reached an unprecedented level. Alright, the main content of The Perfectionists has been roughly introduced to you here. According to the author, Winchester, about 250 years ago, as humanity entered the industrial age, it embarked on an unwavering pursuit of precision. From the initial steam engine to automobiles and aircraft, and then to computers and various consumer electronics. These technological wonders, while enhancing humanity's exploration of nature and economic production efficiency, have become increasingly complex, with precision constantly rising. Process standards have evolved from centimeters and millimeters during the first industrial revolution to micrometers and nanometers in today's information age. In the conclusion of the book, Winchester suggests that following this trend, humanity's pursuit of precision in technological progress may enter the quantum era. Concepts of all physical scales, even micrometers and nanometers, may lose their meaning, with time and certain theoretical constants, such as the Planck length in quantum mechanics, being the only reliable measures. The Planck length, theoretically the smallest imaginable spatial scale for humans, is immeasurable and can only be deduced mathematically. If we insist on defining it using traditional physical length concepts, one Planck length is 1.6 times 10 to the power of -35 meters. Of course, materials of such precision are currently beyond human imagination and manufacturing capabilities. Their applications are currently limited to humanity's exploration and measurement of the vast universe, such as the Laser Interferometer Gravitational Wave Observatory, aiming to capture extremely faint energy disturbances known as gravitational waves. If proven to exist, this would provide strong supporting evidence for theories like Einstein's predictions of the Big Bang and cosmic expansion. To perceive gravitational waves, two massive lasers are employed. If gravitational waves from space pass through the Earth, they cause extremely subtle disturbances to the lasers. To capture these minute disturbances, scientists have installed what is claimed to be the most precise measuring instrument in human history, in the central part of the observatory. It is a perfectly shaped cylinder made of pure quartz. By continuously reflecting lasers, this instrument helps scientists detect minute changes in the distance traveled by laser beams, allowing them to determine whether gravitational waves have arrived. How precise is this device? If used to calculate the distance between Earth and the nearest star, Alpha Centauri a journey of over 41 trillion kilometers, the length can be measured with precision down to 60 to 90 micrometers, which is the diameter of a human hair. It can be affirmed that humanity's pursuit of precision, like its exploration of the natural world, is boundless. This concludes the essence of the book. Congratulations on completing another book. Thank you for your support and attention. Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with friends around you. Let us combine wisdom and practice to achieve our financial goals and create a better future together. Thank you all, goodbye.